maybe that's a clue, because 5 is a lot less than infinity. If we turn it into a literal spherical cow, it has a ratio dimensions that comes out to be the magnitude of the cosmological constant, meters squared. I need your help. What's going on here?
You finally flipped.
So, welcome everybody. All right, so today we're going to be talking about this fun little quote here. It's called the spherical God cow, whatever that means. So we're going to go into that, and we have our terribly drawn little friend here that's not quite spherical, but this is a bit of a pun on the whole concept of the spherical cow within physics, because physicists very often, well, we treat it as an idealized condition, even though things are usually never actually idealized. Okay, and then I called it the God cow, of the play on the God particle, because it's something that happens to annoy a number of physicists, even though it was written by a Nobel Prize winning physicist who most likely probably did it to sell more books. So that's where the term comes from, and it's a crazy title, but we're going to kind of go into precisely why I named it this. And also we do have a new shirt for those of us in attendance. Hopefully I did have enough sizes. Mike, I'm sorry, I can order you a couple of more. But basically this just has the equation that I presented over in Portugal on an episode of Paradigm Drift. Again, this is a claim that the elementary unit of action divided by the reference action, you take the square root of that, multiply it by a Planck mass, and coincidentally you get really good agreement within about 4 mega electron volts of the most recent measurement coming out of the CMS detector. For what we're going to be talking about here, don't need that at all. You can literally just go on Wolfram Alpha, do some calculations, and see what we're talking about. Okay. So the whole claim is, what the heck is going on? Now, part of this is, and I kind of wanted Dan and Jim to be here because I know you guys are really both into cosmology and everything, because I play around, I go down so many different Wolfram holes, so to speak, that a lot of them are just dead ends, don't really go anywhere. I feel like I'm just a crazy person. I mean, that's true, but at the same time, every once in a while, maybe you find something that's a gem. Maybe it's just fool's gold. I'm totally willing to accept that to be the case, but I'm going to need everyone here's help once we go through this to try to kind of brainstorm what the heck's going on. So let's get into it. So basically all I did was I took the mass of the Higgs, so just lowercase m, subscript h with 0 because it's spin 0 particle. So now we have a mass. Now it's very often measured in mass energy, so we'll just, for accounting, c squared. So we're taking the mass energy equivalent of the Higgs boson. Okay. Now we're literally going to turn it into a spherical cow. We're going to do 4/3 pi r cubed, and then we're going to do, for our r, we're going to do the I think this is the symbol for the Compton wavelength of the Higgs. That's cubed. So literally we've taken mass energy of the Higgs boson and we are turning it into a spherical cow. 4/3 pi r cubed. Okay. This equals very big number. Big number. In the video, I'll probably just overlay the exact calculations, but just for sakes, it gives you a really big number. Now, this number is in its energy density. So we have energy density. So basically, it's an energy divided by a volume. And we are assuming it is a spherical cow. So I'm like, okay, what do we do with this? Is there anything else within our realm, so to speak, that's important, that has energy density? Well, we happen to have the universe's energy density as measured by Planck and everything. And again, I'm assuming that they measured something, their detectors went click, things seem to work. Okay, I'm assuming that most of physics generally works, and again, there's probably going to be some tweaks there. We know that it's not the final answer, but if we have the density, so we'd have rho vac, and if we take this number and then we divide it by little cow here, so if we take the vacuum energy density, we divide it by this spherical god cow, we get approximately 1.1 times 10 to the minus 52. Okay. I look at this and I'm like, wait a second. Why does this number look so familiar? Coincidentally, the cosmological constant, I'll just do spell it right, Cosmo. If you divide this, oh, excuse me, we need to do this the other way. Inversing matters. So, no, actually, this was the right way. So, basically, we get this number. This is a dimensionless number. I was doing it right the first time. Cosmo is approximately 1.1 times 10 to the minus 52 reciprocal meters, so inverse meters. So square meters with a 1 over it. Okay. What the heck is going on? This is why I kind of wanted to present this, because it's like, okay, at one point, little background of the story, one point, probably, I don't know, maybe about a month ago, Professor Sean Carroll put up one of his solo Mindscape podcasts, and in a row he was talking about the problems within physics. He's like, well, you have the hierarchy problem of the Higgs boson. Why is it so much smaller than the Planck mass? Again, I would claim that maybe there's a reason for that. That aside, literally just putting in the words on Wolfram Mouth, and again, it doesn't have the most up-to-date measurements, but to first level rough approximation, why the heck should the one, to our knowledge, something that we believe to be the Higgs and have Higgs-like properties, and that's an elementary scalar boson that we believe, according to the standard model, that suffuses all of our realm. It just seems to be everywhere. It seems to help give mass to other particles. That is what we believe it does, and we believe it's everywhere. If we turn it into a literal spherical cow, it has a ratio dimensions that comes out to be the magnitude of the cosmological constant. If you divided these into each other, you would basically get a difference of, depending on which one you divide it into, meters squared. Which is an interesting thing, because as we played around with some toy models, that seems to be the difference between different ratios. It's just meters squared. Guys, I need your help. What's going on here? Thoughts, comments?
Question.
Yes.
How many more digits is this true for?
This is, okay, full disclosure, I'm writing it about, it has the correct magnitude. The cosmological constant depends on the data set you adhere to. So it appears that if you would include supernova data from farther and farther away, that number, that 1.1 can go up to, I think I calculated about 1.4 or so. So that's part of the crisis in cosmology.
So we don't even exactly have a nailed down concept for it. So as well as you can tell, that's with the data right now.
Yeah, so generally this number has pretty good agreement with like the Planck survey and things that are closer to us. So unless maybe universe is rotating, which I'm a little bit partial to, but I don't know that's the case, or unless there's a very good estimate or explanation for why our data starts to deviate at greater and greater distances. I just thought it was very interesting that it seems to, like, basically this is kind of the lower end there. This actually comes out to be I think about 1.083-ish, something there. So it seems to have pretty good agreement with what we believe to be the cosmic microwave background. I mean, I just saw this. I did a calculation. I'm like, wait a second. That's not basically the magnitude, because Wolfram Alpha rounded in there. So I'm like, it literally gave me 1.1 times 10 to the minus 52. And then you type in cosmological constant. It gave me 1.1 times 10 to the minus 52 reciprocal meters squared. And I'm like, that's weird. So, oh. Hello, sir.
Hi.
Do you have questions, comments?
Yeah, I have a comment. I noticed that the spherical cow is a spherical ball.
Oh.
It's full, right? It's not just a shell, it's full. And then as
R cubed. Yes. Yeah.
So when I think of the full ball, I also think of the boundary.
Yeah.
The divergence in the ball and the flux through the boundary. The boundary can be a square thing instead of a cubic thing. So you might maybe somehow have seen something going through a boundary of the spherical god cow. So maybe the spherical god cow's skin has something to do with this meter squared thing. And the spherical god cow's body has to do with the Higgs. But that's so far removed from reality, I have to call it complete utter speculation. Utter speculation. So take that for what it's worth.
Okay. Yeah. All right. No, thank you, sir. Thank you, sir. I mean, hopefully, I am of the opinion that observers like us, human beings, we should be able to figure this out. Maybe not today, maybe not tomorrow. Who knows? Maybe Wednesday or Friday we'll figure it out. I couldn't say. But yeah, I just did this calculation. I'm like, wait a second. And I think, was it Professor Carroll or anything? He said something about it's like, oh, you have these differences. Oh, they get this magnitude or something. I don't think maybe he said they were of a similar magnitude, but it would depend upon your units and everything there. I just generally use the 5 general bases that is laid out: time, space, mass, charge, and temperature for my own parameterization, because I'm like, well, if we can reproduce our observed values using only 5 bases, maybe that's a clue, because 5 is a lot less than infinity.